Hello, and welcome back to our series on electrical and computer engineering. Our conversation tonight is about sources transformations. 2 videos ago, we learned how to simplify 2 elements in series and 2 elements in parallel. However, that very evening, I warned you that most of the time elements are neither in series nor in parallel. That's why we've learned to identify a y of elements and transform that into a delta of elements, and a delta convert that into a y. Why is that? So we can continue simplifying elements in series and elements in parallel. That wasn't enough. That's why tonight I will show you how to transform a branch like this one into a pair of elements like these two. Why do we want to do that? Yes, we want to continue simplifying elements in series and elements in parallel. Remember, when you're simplifying, do not oversimplify. If you know in advance that you will be needing the current, the voltage, or the power in a given element, do not simplify that one element. Leave it alone. With that caveat, I think we're ready. Let's begin.
If we have between nodes A and B a voltage source in series with a resistor R, we can replace that by a resistor R in parallel with a current source Is of an unknown value between the same 2 nodes A and B. The question is, to guarantee equivalence, how do we know what values we should use for the resistor and for the current source Is? Easy. We keep the same value for the resistor in ohms. And for the current source, we divide the value of the voltage source by the value of the resistor, and that gives us what should be the value of the current source if we want to guarantee equivalence between the circuit on the right and the circuit on the left. And what if we want to go the other way? Let's say we find in our circuit a current source Is in parallel with the resistor R between nodes A and B, and we want to replace that pair by a branch with a voltage source Vs in series with a resistor R. How do we achieve equivalence? Easy. Keep the value of the resistor in ohms, the same ohms here and there. And what about the value of the voltage source in this case? Multiply the value of the known current source by the resistance, and that gives you Vs, the value that you should use for the voltage source to guarantee equivalence between the 2 sets of elements. Easy enough, right? But we better see that in action in a numerical exercise. Now let's go into some numerical exercises. Tutorial time number 1. This exercise was taken from the excellent McGraw-Hill book by Drs. Alexander and Sadiku. In this exercise, we're asked to find the voltage Vx between nodes A and B. How much higher A is than B in that diagram? Well, in this circuit, we realize there are no resistors in parallel, no resistors in series. How am I going to simplify this? Well, how about these 2 elements in series, right? That is an RV branch, and we know we can replace that with a current source in parallel with a resistor. And how about this other one? Same deal. We can replace that by a current source in parallel with a 20 ohm resistor. Let's do that. Let's take the one on the left. This one. This one on the left would be a current source with what value? 50 volts divided by 10 ohms. That is 5 amps. And the same 10 ohms resistor. 5 amps and 10 ohms resistor. How do I know the direction for the current source? Well, it follows the minus plus direction of the voltage source, right? That's the one. Well, we have already replaced the one on the left. What about the one on the right? 40 volts divided by 20. That is 2 amps. And the same 20 ohms like this. 2 amps and 20 ohms. And the direction of the current is given, of course, by the polarity of the voltage source. What can we do now? What have we won? That now we have these 2 resistors in parallel, and we can simplify them. 10 in parallel with 40. Remember, that was 10 times 40 divided by 10 plus 40. That is 8 ohms. So we have 8 ohms there. What else? Those two current sources, 8 amps and 2 amps, they are in parallel. So we can add them up, and we have a single current source of 10 amps. Let's redraw the circuit like this. 8 ohms and 10 amps on that side. Are we done? Of course we're not done. We want to continue with the simplification. Well, what do we do now? We just realize, hey, a current source in parallel with a resistor, we can replace that by a voltage source in series with a resistor. So we take this one and we will transform it. And we also take this group and transform them. What's going to be the one on the left? Let's see, 5 times 8, and that is 40 volts in series with 8 ohms. Fine. This one, right? 40 volts in series with 8 ohms. What about the one on the right? 10 times 20, that is 200 volts in series with 20 ohms. There you go. What is next? Now we simplify those two voltage sources in series, that is 200 minus 40, because they are, of course, they are in series, but they are opposing one another. 200 minus 40, that is 160, and 20 and 8, those are in series, that is 28 ohms. This is our simplified circuit. And now, shall we simplify the 12 ohm resistor as well? We could, but we should not. Remember, don't oversimplify. Do not simplify the element into which you want to know what are voltages and currents. Leave it alone. Let's solve this circuit. Can you tell me what is the direction of the current in that circuit? Of course, the voltage source is imposing current to flow this way. What is the value of that current? Well, you say the value of the voltage source divided by the total resistance, 12 plus 28 ohms. That is 4 amps. Now, those 4 amps will produce an ohmic voltage drop in the 12 ohm resistor with this polarity. Agreed? VW. How do we compute that voltage VW? Ohm's law. Ohm's law. Multiply the resistance 12 ohms by the current 4 amps. 48 volts. Are we done? No, we're not done. I've computed V sub W. And the problem is asking us Vx. And Vx is the negative of VW. So Vx is negative 48 volts. And now we're done with that exercise.
Prove it, eh? Now you challenge me to prove all this. You want me to show that it's true that if we use the conversion formulas that we have just seen, the parallel of the current source and the resistor is equivalent to the series of the voltage source with that resistor. But equivalent? Equivalent how exactly? Well, let me give you a couple of analogies that are hard to forget. Both are a little bit cruel and extremely ridiculous. Why? Because we humans, we rarely forget cruelty or ridiculosity, which I promise, it is a real word. In a parallel universe, in an alternate reality, you look like Brad Pitt, and you have a date tonight with Angelina Jolie. You arrive at the restaurant all dressed up and find that Miss Jolie could make it and send a replacement in her place. Personally, I find Mrs. Clinton extremely attractive. However, Brad Pitt may not think that this is an equivalent replacement. But if instead of Brad Pitt you looked more like a hungry Siberian tiger, you might find that replacement perfectly equivalent, because after all, a meal is a meal. Another one? Sure. Remember this scene from the genius of George Lucas' Riders of the Lost Ark? Indiana is trying to find an equivalent for the golden idol. Equivalent how? An object that has the same mass. You and I know how well that went, eh? Now, in an electric circuit, what do we mean by equivalence? When we say that a group of elements is equivalent to others. Let's say we have a big circuit, and between nodes A and B of that circuit, we have that blue box connected. And we want to replace the blue box by a red box. And we want the red box to be equivalent to the blue one. What do we mean by that? That the current is the same in both cases, and the voltage between nodes A and B does not change. Why? Because electric circuits have no ears and no eyes. As long as the current and the voltage are the same, the circuit will not notice any difference, any change, and both boxes, the red and the blue one, are deemed equivalent as long as the big circuit concerns. So what we need to demonstrate is that when we replace this branch with this pair, the current is the same and the voltage is the same as well. In the circuit on the right, let's analyze and try to find what is VAB in terms of the current I. Do you agree that because in a passive element, current flows from higher voltage to lower voltage, that the current I is producing a voltage drop with this polarity? Absolutely. And what is the value of that voltage drop? Ohm's law, R times I. That means that node M in the center is higher than B by the value of the source, Vs volts. M is higher than B at the bottom by Vs volts. And A is higher than M by Ri volts. So if we add those two voltages, we get the voltage between A and B. Absolutely. A is higher than B by all of that, Ri plus Vs. And in the circuit on the right, let's see. If we apply KCL to that little Gauss surface in there, we can determine what is the value of the current IR in the resistor, which is, of course, using KCL, the sum of the current I in the branch plus the value of the current source Is. And now we can use Ohm's law to compute what is the voltage VAB, which is the voltage in the resistor, R times I. R times IR. But if we replace this value for the current in the resistor and we expand, we distribute that multiplication, look what we get. The voltage VAB in the circuit on the right is the sum of Ri plus RIS. But that voltage needs to be the same as the one we got for the branch on the left. But for them to be the same, obviously, these two terms need to be equal. Vs has to be RIS, or what is the same Is is Vs divided by R, which is what we wanted to demonstrate. To achieve equivalence, that is the relationship between the value of the voltage source and the value of the current source. And that, my invisible friends, is all for tonight. I hope you have enjoyed this video as much as I have enjoyed putting it together. I invite you to join me for our next video. Have a very good night.